Welcome back. Hi, Dan Linehan here again with ATA Engineering. Today we're going to delve a little deeper into the technical aspects of ground vibration tests, or GVTs, and expand on ATA Engineering's testing methodologies. In part 1 of this series, I gave you a brief introduction to the ground vibration testing of aircraft and some reasons why these tests are important in the aerospace industry. As we discussed, during a GVT, we quantify the ratio of output accelerations at many discrete points on an aircraft to the input forces that were applied. I briefly touched on the methods that we use to gently apply input force to an aircraft, but it is also important to understand the history of these tests and the current state of the art for these methods so that we can remain innovative and adapt to our clients' needs in ensuring the safety of their aircraft. For the original aircraft GVTs in the 1960s and 1970s, input force excitation was very simple. Test engineers applied a sine wave with a specific frequency input at strategic locations on the airframe and adjusted that frequency until they excited a vibration mode of interest. Engineers had to search for the correct frequency by manually watching what is called a Lissajous plot on an oscilloscope. If the plot became a circle, they knew they'd found a natural frequency of the structure. To find all the frequencies, they would have to move shakers, move sensors, and repeat the search for every mode they expected to find, one at a time, day after day. Using this method to extract target vibration modes of the aircraft was quite time-consuming, so new methods were developed. Later on, instead of tuning sine wave force inputs at every target mode frequency, newer GVTs employed a sine wave with a slowly varying frequency, starting low and sweeping up. The full sweep would envelope the full range of target modes, thus saving significant time in conducting a GVT. However, if you needed to resolve 2 or more modes of vibration whose frequencies were nearly identical, test engineers would need to relocate the input force location to excite each mode separately. Test engineers would then reapply the sine-sweep force input and take more data so that each mode could be successfully acquired. So this was faster than previous methods, but still pretty time-consuming. ATA's predecessor, Structural Dynamics Research Corporation, which you may know as SDRC, realized that they could significantly decrease test time by using multiple force inputs of broadband noise that encompass the full frequency range of interest and applying them at the same time on different locations on the aircraft. A few examples of different locations could be the 2 wingtips, all of the engines, and the tail of the aircraft. Essentially, because the force signals are broadband random noise, they're independent of each other, or uncorrelated as we say, so in theory, all target modes can be extracted in a single data collection run if you apply the input forces at the right places. This ultimately saves a lot of time during the test. This SDRC technique, called multiple point random, or MPR, was widely used starting in the 1980s and is still one of ATA's preferred excitation methods when performing GVTs to this day. But while MPR significantly reduces test time, it does come with a trade-off compared to sine wave excitation methods. Specifically, MPR's broadband excitation is less energetic at any given input frequency, which of course includes the frequencies for all of the aircraft's target modes of vibration. As a result of the less energetic broadband input, extracted modal parameters from weakly excited modes will have less precisely estimated modal parameters and modal mass. So I know what you are certainly thinking. Wouldn't it be awesome if we could combine the excitation energy inherent to sine-sweep force excitation methods with the schedule efficiency of uncorrelated MPR force excitation? Luckily, ATA can and does do just that with our patented multi-sine GVT method. Multi-sine is as the name implies. We apply several sweeping sine wave inputs to an aircraft in the same data collection run, but at any given moment, the sweeping sine waves all have different uncorrelated frequencies at each input force location on the aircraft. In this way, in a single data collection run, we can achieve robust input force energy and full target vibration mode frequency spectrum excitation with a sufficient quantity of the input force reference locations necessary to resolve and extract all target modes, whether closely spaced in frequency or not. At ATA Engineering, we are always striving to develop and implement innovative methods that will aid our customers in overcoming engineering challenges to achieve solutions that positively impact the world around us. With the development of ATA's multi-sine GVT excitation method, we are able to execute these tests effectively and efficiently for the success of our customers and the safety of their aircraft. If you're interested in learning more about ATA's testing capabilities, visit www.ata-e.com or connect with us on social media.